we see a screen. Right. All right. So our today's speaker is Aygerim Kalijanova from Nazarbayev University in Kazakhstan, and the title of today's presentation is Modeling Tuberculosis Transmission Dynamics in Kazakhstan using SARIMA and SIR models. Please, Aygerim, you can begin your presentation.
Thank you, Professor. Good morning, everyone. I'm sorry. Good afternoon, everyone. Thank you for being here today. It's an honor for me to present our work. This work is actually the joint work with fellow students and our professors. And this research is funded by the Committee of Science of the Ministry of Science and Higher Education of the Republic of Kazakhstan. Okay, let me begin. Okay, this is the content of my speech. I'll give a brief introduction about what TB is and about the models. I will talk about the objectives of the study, the materials and methods we used. After that, we will discuss the results and accuracy test results. Okay, let me begin with an introduction. So TB remains a major public health issue worldwide, particularly in developing countries. It is caused by the Mycobacterium tuberculosis. It damages mostly lungs and sometimes kidney, spine, and brain. It transmits through air, and it can be treated by a combination of antibacterial medication with DOTS, where DOTS is the directly observed therapy. Okay, Kazakhstan has made a significant progress in TB control, but challenges still persist, especially with the drug-resistant tuberculosis, where we see that the treatment success rate, according to the latest data, is around 88% for drug sensitive and 77% for drug resistant TB. Okay. Although these statistics are quite positive, we would like to understand the TB dynamics in Kazakhstan through simple statistical, SARIMA, and deterministic models, SIR. Also, we would like to compare models' ability to forecast the disease dynamics. Okay, let us discuss the materials of the study. So this is a retrospective quantitative study located in Kazakhstan. We used the data from the Unified National Electronic Health System, which was launched in around 2005, I guess. It contained the data set. The data set contains the patient data, number of patients diagnosed with TB in the period between 2014 and 2019. And the data patients were classified into two classes. First one is A15, which is defined as respiratory TB confirmed bacteriologically and histologically, while A16 is the one which is not confirmed. So it means that symptoms of TB persist, but various medical tests couldn't identify this TB bacteria in the blood. Yeah, let us look at the data we have. We plotted the dates versus the number of TB patients. For two different classes. The first one,
sorry, please. This is absolute number for all peoples of Kazakhstan or partial cases, absolute number of ill persons or another. TB cases.
Yes.
Absolute number of ill peoples in Kazakhstan, around Kazakhstan, or several cities.
It's all around Kazakhstan.
Total number of ill
people
TB
in the country.
All. This is
Yes.
not divided by all population in Kazakhstan. Absolute number. Yes. Yeah. Thank you.
Thank you. And we observe this on these plots, the decreasing trend in the number of cases, and we will further look for the reasons and mathematical, of course, reasons and the future of the dynamics. So the first model we'd like to consider is the SARIMA model. This is a statistical model that is used for time series forecasting. It captures both autoregressive, differencing, and moving average components, along with seasonal variations. So each letter here, P, D, Q, and capital letters, they stand for a certain notion. P is the number of autoregressive terms. D is the number of differencing steps required to make the data stationary. And Q is the number of lagged forecast errors. Capital letters stand for seasonal counterparts of these. And S stands for the length of the seasonal cycle. Okay. Next one is the basic SARIMA SIR model. This is one of the most popular and fundamental model for compartmental modeling. Each letter here, S, I, and R, stand for susceptible people who can get infected. I stands for infected people who transmit the infection, and R is the class of people who recovered from the disease. And the transition between these compartments is governed by these two basic parameters, beta and gamma, where beta is the infection rate and gamma is the recovery rate. So as you might know how this infection happens, an infected person and a susceptible person, they meet, and most probably with a probability of beta I over n, the susceptible person gets infected. One more very important parameter is R naught, which stands for the basic reproduction number. It's the number of secondary infections that a single infected person can cause. So after some analysis, after some calculations, we get this expression beta over gamma. So if this R naught is less than 1, then we say that the disease persists. Disease-free equilibrium is stable, so there is no endemic. And if R naught is greater than 1, then the disease persists. Okay. So further in the analysis, we will calculate the values for each of the parameters. Now, model fitting results. So we tested multiple SARIMA models and selected the best performing one that is based on archaic information criterion, also known as AIC, and the Bayesian information criterion. So according to these plots, we can see that the final SARIMA model effectively captured TB seasonality. And these plots explain that the residuals are, most of the residuals are explained by the model. So these for A15 and A16, these are quite similar. We can only see a few outliers by the tails of the plots, but this is, we think, natural for the real case data set. And now we fitted the SIR model. As a result of the fitting, we got the parameters beta, gamma, and R0. As you can see on this table, all of them are less than 1. So from R0 being less than 1, we are convinced that the TB dynamics is decreasing. And from the beta rate of infection, we also conclude the same result. Some of the values for these variables SIRN were retrieved from the data, and some of them were calculated.
Sorry, I have a question for understanding. What is the dimension of parameter beta and gamma? Dimension, days, years, or another day, or what is the dimension of these parameters in your real data? Dimension. Размерность. Размерность. Сутки. One over day, 1 over year. What is the dimension?
It's per year. Yes.
Per year. Per year.
I'm sorry, per day. That's a per day
per
data.
Day?
Here. Yes. No, monthly, per month. I'm sorry.
Dimension of coefficients per month.
Yes, per month.
Thank you.
Thank you for clarification. Okay. So as a result of the fitting, we get this fitted curve, which is highlighted in green. And we can see that the model more or less captures the decreasing trend. However, these fluctuations are not captured well. Further, we will use these fitted parameters to forecast the model, the dynamics of TB. This is the simulation of all 3 compartments, where blue is the susceptible compartment, red infected, and green is the recovered compartment. Okay. After the fitting, we used the fitted parameters to forecast the model dynamics. Here you can see the SARIMA's forecasting result. Until 2020, like 2019 December, we have the data. And after 2020, in this plot, we can see the forecast of the SARIMA model. In the blue line is the main plot, and this red range is the confidence interval. So we can observe that SARIMA not only forecasts one case, but it considers the upward trend or even a downward trend. Okay, I will show you the table with accuracy tests a bit later, so it will be more clear. Okay. Oh, and I forgot to mention that these accuracy tests were conducted using also by comparing these forecasted data points here and actual data points here. This is the forecast from SIR model. We can see that it cannot capture these seasonal patterns and fluctuations, but still persists, still the decreasing trend persists here. Okay, let me show you the numbers. That would be more clear, I guess. Okay, so we used most, I would say, popular metrics, R-squared, RMSE, MAE, and MAPE for each of the models with respective classes of data, A15 and A16. So we can see here from the table that SARIMA shows a strong predictive accuracy with an R-squared being 89%, 0.89 for A16 class and 0.76 for A15 class of data, which means that 76 and 89% of data were explained or forecasted correctly. And the model effectively captured the seasonal fluctuations in TB incidence. So I concluded from this R-squared and other metrics that it did a good job. So, but looking at the SIR accuracy results, it is twice less than SARIMA could explain for A16 data, as we can see here. It's only 42% and 61%, which says that SARIMA model is not really suitable. SIR model is not really suitable for forecasting the dynamics of the TB. However, SARIMA might be the case for us. And also an interesting observation here for RMSE and MAE, which are much greater than 100%, just 174 and 160 or 46 for SIR A16 data. We assume that this happened. Where is the plot? That there are a lot of fluctuations here that cannot be explained by SIR model, simple SIR model. Although it's nonlinear, it might need adjustments to better capture these peaks, seasonal peaks. Let me check this. Okay, so as a result, we see that a decreasing trend in TB notification rates in Kazakhstan is captured by both models, while SARIMA shows explains exactly the seasonal fluctuations, and SIR model, although not able to capture seasonality, it gives us insights into the underlying dynamics of the infection spread. And we believe that this work might be a ground for future studies with better models and might even be co-infections or more complex SIR model And also, we confirmed that the SARIMA model can be used for forecasting the TB dynamics. I guess that is it for my talk. Thank you very much for your attention, and please, if there are any questions, happy to answer them.
Yes, thank you, Aigerim, for this presentation. Indeed, we have time for questions and discussion. So please, from our audience, if there are questions, you can ask. And I have a question about slide 11. So please, slide 11.
Okay, let us see slide 11. Yes.
No, I am wrong.
Isn't this?
No, not this. I don't know. Maybe the next one where you have this installations data with installations. Slide. Yes. Yes.
This one?
Yes, this one. It's not 11. It's 10. Yes, sorry. So this installations, you say that it is seasonal, or what is that? Because
yes.
Because if you look, what? So indeed, we see that 2015 is probably winter 2015. There is an increasing of number. Also 2016,
Yes.
but for later years, it's not clear. There are no such clear dependence on the time of the year. And moreover, there are looks like there are several oscillations during 1 year. So how to verify that? Well, intuitively, we can imagine that in the winter time, there might be more cases, but can it be really verified with the data?
This might be the case where we need more data, because the data we have is just about the number of cases, and that's all. I think if we had more the variety of parameters, that would be possible, I think.
And moreover, in this second figure, right figure, well, also, well, there are quite frequent oscillations, so it's not really clear whether it is related to different seasons of the year or not. So, all right. So, related question is, people who have treatment, how much time it takes to recover?
It differs. As far as I know, it might be 6 months or 3 months, or even a few years.
Yeah, but this data, this number of people, these are new cases or all registered cases at this moment of time?
These are, I guess, new cases.
So new cases during every month, right? You don't count previously registered cases, right? Only new cases.
No.
All right. But also related question. So as an estimate of how many people,
Vitaly,
yes.
Sorry.
Yes.
Repeat, please. This data on this slide means the new cases of this year. New cases.
Yes.
Not total number of ill people. These new cases which have been tested from people, new cases per month. Yes.
Yes.
New cases, and if we integrate, we will have a total number of population. I understand. No, the new cases. New. No, I am understand. This is new cases. Yes. Right.
Yes.
Thank you.
Yes.
Sorry, Vitaly. Sorry.
No problem. Please, if you have questions, you can ask. But for example, if we take 2015, probably the first point in 2015, maybe it's January 2015. So there is about 1,000 new cases, right? In the left graph, if you take 2015, yes, it's about 1,000 new cases in January 2015. This is probably how we can understand this graph, and probably maybe not exactly, but looks like there are about maybe 12 points for every year. Then it's monthly data. All right.
Yes.
Do you have estimates of how many unidentified cases? So how many people who can have tuberculosis but who are not identified?
No. Everything comes back to the lack of data.
All right, and then
we don't have that. Yes.
I finish with this slide. So then slide 12, I believe slide 12, please, where you show the model. Yes, this. Yes, yes, of course, we are familiar with this model. But I have a couple of questions here, because when you consider this model, what you suppose about tuberculosis, about people recovered from tuberculosis? Do they have immunity, life immunity?
Yes.
All right. So, well, it's of course a hypothesis which might not be, of course, valid for several reasons. One of them is that after some time, acquired immunity decreases, and I suppose that people can be ill, can have tuberculosis just more than one time in their life, and certainly there are different strains of tuberculosis.
Yes, I totally agree with you. So the idea behind using exactly this model is that we wanted to see if it's possible to describe the dynamics using the simplest model possible.
Yes, I understand.
Yes.
But here in the slide, you write that if R0 basic reproduction number is larger than 1, then endemic equilibrium is stable. But this does not correspond to the hypothesis of the model, because in this model, I always converges to 0 for large time, because there is life immunity. So there is no endemic equilibrium. There is no positive equilibrium here. Please pay attention to that. So the value of the basic reproduction number less than 1 or larger than 1 gives you the condition of the emergence of this epidemic spike, whether the epidemic will progress or not. But even if there is epidemic, after some time, the number of infected goes to 0. You understand?
Yes, thank you for pointing that out.
All right, now then show please slide 14. Truly speak, yes, 14.
This one? 14.
No, 14, yes, this one. Truly speaking, I don't understand what is shown here. So for example, this histogram upper right, what it shows here?
It shows the distribution of residuals and the data.
No. What means residuals? And so could you explain a little bit? I really don't understand the meaning of this graph.
So we have the data. Yeah. For the SARIMA model, it has to be standardized. So the standardized is this pink or yes, plot the normal distribution, right? You can see here. So we need our data to be distributed normally or close to normal. And this plot histogram shows how the data is distributed. So it is close to the normal distribution, so we can continue
normal
dealing
distribution
with
of this. Yeah, normal distribution of what? What is on the horizontal axis here?
Actually, this part of the analysis was done by my colleague. So the only thing I can tell about these graphs is that, in general, the data is ready for the further analysis.
Well, all right. Maybe I just don't know that. Maybe other people understand better. But okay. Yes. Then slide 23, please.
This one.
Yeah, you explained this table, and in particular this some percent. You said you told us more than, for example, for the SIR model, more than this RMCE, more than 100%. But what is RMCE, and what means that it is more than 100%? Could you please comment on this?
RMSE is the root mean squared error. So let me, can I show you the formula for it? Oh, okay. I guess it would be faster if I show you on Google.
Well, I suppose maybe this is not necessary. So it's difficult to explain like that.
Yeah. Okay. So RMSE in the ideal case must be less. Like here for SARIMA, it is 46, 68. So
all right,
the maximum value.
Yeah, this is kind of a measure of deviation of the data from the model. What is what? Okay.
Yes, it's the average difference between the statistical model's predicted results and the actual results.
All right, this is more or less clear. Okay, so SIR model shows not a very good agreement, at least for the last one, right?
Yes.
Yeah. And one of the hypotheses, I think you mentioned maybe, that it is related to seasonal deviations, right? To seasonal oscillations. This is what you
Yes.
But you know that you can introduce the seasonal variation in the SIR model.
Yes, I've read a few papers with that.
You just in the coefficient beta you can put time dependence, because beta, as you explained, characterizes disease transmission rate. Disease transmission rate depends on the time of the year, because our immune response, our immune system depends on the time of the year. In winter, it is weaker than in summer. So this is why such diseases can be more easily transmitted in the winter. So beta, in fact, can be considered as a periodic function of time.
Yes, you're totally right.
All right, I don't have other questions and remarks. Please, other questions from the audience? Well, if no other questions, then yes, Ivan, do you have a question?
Yes. Can I ask you the following question? So you showed the ACF plot on page 14, the correlogram plot. And you said that it has an explicit seasonality However, this graph does not actually show this because, as we can see, it is equal to 1 at point 0. However, it is always equal to 1 at point 0.
First of all, about what graph you are talking?
The last graph, the fourth graph, parallelogram plot. So it doesn't actually show the seasonality in the data.
Oh, that's interesting.
Do you have exact seasonal parameter value in SARIMA model?
As I said before, this SARIMA model was evaluated by my colleague, and I don't have like details of the model.
Okay.
I may ask him if you are very interested.
All right, other questions?
I have one question.
Yes, please.
If the tuberculosis is seasonal disease, I didn't know this.
Is tuberculosis a seasonal disease?
Yes, you talk about seasonal differences, but I thought that it's seasonal disease.
It is seasonal because it mostly appears in the winter season, as far as I know. And according to the data, there are like, where is it? For some period of time, we can see the peaks by the end of the year. For example, 2014 December a peak, 2015 December peak. So December, January. Yes.
So data shows that it's rather seasonal.
Yes. Yeah. It's more yes than no.
I didn't know this. Thank you.
Thank you for your question.
Other questions, please?
Can I ask one more question?
Yes, please.
Yeah, sure.
So we basically have only monthly data, so we cannot say that there is, for example, weekly dependence. By dependence, I mean seasonality, or I don't know, 2 weeks dependence, and so on. So the minimum range is months. So that's why we can only like say that there is at least monthly or yearly dependence, seasonality. Sorry.
Yeah, it depends on the data. We only have like monthly data. That's why we used exactly this per month. But I think it can be at least weekly.
No, I mean if we only have monthly data points. So this graph is monthly. So if we do not have like daily data points, we cannot determine weekly dependence.
No, but yes,
Most probably no.
No weekly data, but still, even for monthly data, in principle, it is possible to just evaluate like seasonal dependency if we take winter months or summer months.
However, for 2017, it seems there is no seasonality, or for 2018,
Yes, this is
peaks of the same size in the.
This is right, right. But I think that more detailed statistical analysis might show whether there is this seasonal.
There might also be like external. It might be influenced by external factors. For example, there might be a new strategy of treatment or prevention. for example, any policy by the government to prevent the TB cases. So there might be.
Yeah, by the way,
different.
I think that in one of the first slides you showed dynamics of this disease for later years, 20 and 23. Could you please return? I don't remember which slide, but I think at the beginning you had something like that.
This one?
No.
No?
Yeah, wait.
Uh-huh. Okay. This one, right?
Yeah, this one. Yes. It's incidence rate. You see, you have this data for years 20 and 23, and it looks like you don't have this decrease anymore, and that it stabilizes at some. Well, of course, it's difficult to judge if you have only two numbers for the year 2020 and 2023. But okay, if I can make conclusions from only two numbers, it looks like that it is more or less the same, and there is no decrease anymore. At least there is this strong decrease in the beginning, but no decrease later. Of course, again, these data are not sufficient, but is it possible to get additional data and to check maybe there is really an endemic equilibrium, like a positive equilibrium. So I think that this might be important to check. What is the dynamic? Does it converge to some more or less constant positive value, or it continues to decrease?
Yes, you're right. We are working on that. We are trying to retrieve some more data, and maybe more compartments, data for other compartments, to make this model like more complex and more like realistic. Yes.
Yeah, but
there is a possibility. Yes.
The main question is that if the epidemic continues, if there's really an endemic positive endemic equilibrium, so important question is why? What is the reason for that? And there are different possible reasons for that. And you can suggest like different models giving such result, but you will never know whether this is true or not, because you need really the understanding a possible explanation, at least the hypothesis of why it is like that. Otherwise, you can suggest like five different models giving you a positive endemic equilibrium. And how do you know that your explanation is correct? Like for example, what we discussed, it can be finite immunity, not lifetime immunity, or it can be different strain, or it can be a spatial propagation, like in different regions, or it can be resistant cases and which create permanent source of contamination and things like that. So there are different possible hypotheses which might explain the persistence of this endemic equilibrium. I think that this, from the epidemiological point of view, I think that this is the most important question. All right. If no other questions, then thank you again for this presentation. We finished our today's seminar. Have a good day. Goodbye.
Thank you. Thank you for your feedback.